Hello everybody, I'm glad to be here. Today we are going to discuss about needed FCF feature control frame for key assembly. In key assembly, as we can see here, on the right hand side we have key seed, key and key way. On left hand side we can have the first example. We are going to have reference plane A here. It is qualified with this flatness, and then we are going to have reference axis B here. It is perpendicular to A. And here we are going to have reference plane C here for this key slot. And then later on we are going to use ABC to allocate the position of these holes here. Here we have position respect to A and B. That's why we are going to have this basic dimension here. We are going to control the symmetry of these two sides in this key slot here by using this positioning symbol here. It is an assembly. We have key seed, key and key way. We are going to have several standards. We need to follow the standards for this key assembly. Based on application, shape and how we are going to assemble it and function of that, we are going to have several types of key. Let's say song, saddle, tangent, run keys and spline and Kennedy keys. Here we can see this rectangular key and we have this slope here, and then if this cross section is square we are going to use this, let's say, a square key. If we don't have any angle here, if top and bottom are parallel, we are going to call it parallel song key. If we are going to assemble and disassemble the key several times, it is good to use this keep head key. And also we have another key with the name of feather key. We have these two gives both sides, let's say. And if we are not going to transfer that much torque, it is good to use this Woodruff key here. It is related to the geometry and amount of the torque. And saddle key, we don't have any key slot on shaft here. If the surface is flat, we are going to call it flat. If we are going to follow the curve of the shaft, we are going to call it hollow saddle key. It's work based on the friction here. In this figure, we can see it is a round key here, and then here we can see this tangent key. We can see a spline key, and then Kennedy keys are here at bottom right, this corner. Normally, we are going to have 4 different failures in key. Let's say shear, compressive, fatigue, and ferritic fatigue. Let me talk about this ferritic fatigue. We are going to have wear or sometimes corrosion if we are going to have chemical interaction between these two surfaces. These two surfaces we are going to move left and right tangent to that surface, this small oscillatory. We are going to destroy this contact surface between asperities. We are going to make this powder, as we can see in this figure at bottom right. We are going to make this powder. We are going to make this micro crack here, and based on that cyclic load to the left and right side, we are going to propagate that micro crack. We are going to have this crack here. That's why the material, let's say, strength, toughness of that surface is important, and it is good to have this ability for machining. And tolerance is really, really important, and roughness is important, as it is highlighted here for ferritic fatigue. For material, we are going to use carbon steel, stainless steel, copper, aluminum alloy, and mainly for marine industry, we are going to use bronze or brass. Bronze and brass is really good for marine industry. We are going to have several standards regarding to this key assembly. The most common standard is MMC B17.1. We need to have that one, and based on that geometry, we are going to define what should be the tolerances for the key assembly. Here we are going to have another example, another standard. It is GIS B1301-1996. We are going to have, let's say here, tolerances for different key size and let's say key weight. What should be the tolerances for that? It is going to mention. However, if you are going to have thermal load, it is good to consider that thermal load into in into calculation. As we have discussed previously, normally the range of tolerances as we are going to use, it is between G and T. But again, based on the standard, we need to follow the standard, what they say, and we need to consider the effect of thermal load. If you are going to use a screw to fix key to the shaft, again, we need to follow the standard. In GIS, they have mentioned this table for which size of keyway, which size of screw we need to use it. Let's see another example here. We are going to shaft here. We are going to have two Q slot here on left hand side and on right hand side. We are going to transfer the torque from this shaft by this key to this coupling here to another shaft. This shaft coupling is here on right hand side again to next shaft here. We are going to transfer this torque from this shaft to another shaft here. Here we are going to have two references here. Let's say reference axis A and B. We are going to qualify each of them, and we need to connect B and A to each other. And then for this Q slot here, we are going to use this positioning, and TZ is 0.05 with the modifier M respect to AB. And here we have plane C here. Second FCF as needed for Q slot is this perpendicularity. We need to have these two FCF for each Q slot, positioning and perpendicularity. And based on the standard, how we are going to assemble it, is it free tolerance or clearance or interference? We are going to assign what should be the tolerances. For example, here in GIS they say H9 here, and let's say P9, N9. It depends on the application, how we are going to fix key in this key slot in order to avoid fatigue, operating fatigue. However, the material is important, as we have discussed here. The surface roughness is important, the material and the tolerances is important. These three items are really important. Here we are going to have another example. Here we have reference plane A here, it is qualified by this flatness. We are going to have reference axis B here, it is perpendicular to A. Here we are going to have this slot here, and we are going to control symmetry of this slot by using this positioning, and it should be perpendicular to A. And as we can see here at bottom left, we have plane A here, axis B here, and reference plane C here. We are going to have this reference frame here as it is highlighted at bottom right. This frame we have it, A, B, and C. In this slide, we are going to have two examples very similar to each other. On left hand side, we can see this one. We have reference plane A here, reference axis B here, and we are going to have this slot here. And in order to control the symmetry of that slide, we are going to have this positioning control respect to A and B. But on right hand side, what do we have here? We have modifier for reference access B for this hole. It means we have this possibility for shifting because we have B here, this hole. Whenever we are going to have this MMC here, we should have the maximum material on that hole. That's why we are going to have the smallest gauge here, and for different size of the hole, we have this possibility to shift it. We have more freedom here. This gauge size is 12 because for B it is 12.1, and for maximum material condition we are going to have 0.1. That's why for maximum material condition, a smallest hole, it is 12. This gauge is 12. But here, as you can see, for this example, when we don't have any modifier on left hand side, we are not going to use the smallest gauge that. We are going to use the gauge based on that through dimension. But here we have more freedom here when we are going to use this modifier for reference access B here. The last example for today is these two examples here. At top left and at bottom right, we are going to have the same example. Let's see what do we have here. We are going to have reference axis A here. We are going to have reference plane B here. We have this positioning. We need to have this perpendicularity for this surface as it is highlighted by mouse here. And here, in order to control the location of these two holes, we are going to use B here. Reference plane B here. Here, B, this reference plane B, we are going to have this basic dimension 5 here. It means the distance from this gauge for B respect to A is fixed at 5. And then we are going to allocate the location of these two holes here respect to that. At bottom right, we are going to have this translation symbol. What does it mean? What is the main difference between this and that? B is midplane of this slot here. It means we have this possibility to translate this gauge here for B in order to have more contact points between gauge and these two surfaces. Whenever we are going to use, let's say, this key slot as a reference here B, it really makes sense to use this translation symbol here because these two surfaces are small. In order to have more contact surface between gauge and these two surfaces, it's really makes sense to use this translation symbol here. It is another application when we are going to use, let's say, midplane of this key slot as a reference. It is good to have this translation symbol. For now, I would like to close this session. In coming session, again, I'm going to talk about key slots and another two more standards. I'm going to talk about that, BS and ISO. Thank you for today. I hope you enjoyed. See you next time.